what we're going to do today is not so much on paper. You are going to be watching videos, and I will hopefully be able to narrate them. Hopefully none of them are copyright protected. And if they do, if the video happens to not show up while I'm talking, I still want you to listen to me talking, and then I will have links to the video as well that you can go watch the video without my narration. But I'd like to be able to play and pause as they, in these two different videos, give you some illustrations of apparent magnitude and absolute magnitude. This first one is a model, which is you use objects that are close to you to simulate, to stand for, to act like the real thing. These two lanterns are going to be acting like stars.
All right, so in this demonstration, we are going to be modeling how star brightness is compared to the distance the stars are to us. And we want you to think about, is there a change? Do you notice a change in brightness as stars are closer or farther from us?
Sounds good. All right. You're going to move them?
Now notice these two lights right
So
now
we have
are
two
exactly the
lanterns.
same.
We're letting those represent stars. They're at the same distance. So if you notice, they should look like they're pretty much the same brightness on your screen. Mr. Romig is going to go grab a lantern right now. He's going to move it closer to you. So as he does that, watch what happens. Does it look like it's getting brighter?
Well, even before we think about if it's getting brighter, do you notice which one is moving? That would be the one on the left. And as it moves, watch, does it seem to get brighter? Does it seem to get bigger? They're two exact same lanterns from the beginning.
What's changing?
This is a good place to pause it and refer back to the work that you had done with the pictures earlier this week. You see how some of these stars seem to have more of a glimmer? Those are the ones that we talked about seeming to be brighter and seeming to be larger. Well, now that we get this illustration of apparent magnitude, look at this extra glimmer around this lantern that's closer. It certainly appears larger than the one farther away. It appears brighter than the one farther away. If I would have done this experiment, the one thing that I wish they would have done, I wish they would have showed you both lanterns at the beginning so that you could see they were the same size. But this is really all the video does. There's nothing extra here at the end. After that model, now we're going to go watch another video. This one's a bit longer. It's explained in more detail. You don't need to worry about all of the details. Again, we're after the idea of apparent magnitude, the way the stars appear to look, versus how bright and how large they actually are.
Hi, I'm David Fuller from the Eyes on the Sky video series. Let's look at another aspect of stargazing basics, this time magnitudes of various objects. Now, the word magnitude is just a fancy way to describe the difference in brightness of objects we see in the night sky.
That should be familiar. Magnitude, we've talked about that.
And it's not too hard to learn how it works, but let's start with some history. The Greek astronomer Hipparchus developed the magnitude scale back in the 2nd century BC, when he assigned the brightest stars a magnitude of 1 and the dimmest stars that of 6, the in-between stars 2, 3, 4, and 5 magnitude assigned according to their various brightnesses. Using a logarithmic scale, he assumed that the difference in brightness of stars was 2.512 times brighter than the next dimmest one. Taken across that full 6 magnitude scale, that meant that the brightest stars, the first magnitude ones, were 100 times brighter than the dimmest.
All right, so you don't have to worry about all the fancy math in between. But he's saying the brightest are 100 times brighter than the dimmest. The dimmest are 100 times less bright than the brightest ones.
Or the 6th magnitude ones. It also allows for a fairly easy way to determine other brightness differences. The difference from 1st to 3rd magnitude is 6.3 times, 1st to 4th, 15.8, 1st to 5th, about 40 times.
So if when you were practicing multiplying with decimals, if you ever wondered, will I ever use this? Well, if you go into astronomy and you're working to figure out the brightness of a star, you absolutely need to be able to multiply with decimals.
This worked just fine until Galileo turned a telescope towards the heavens and humans discovered there were a lot more stars out there than just the 1st through 6th magnitude ones that they could see naked eye. But what they did was just extrapolate that scale further. So much like golf or ERA in baseball, the lower the number, the brighter the star, and the higher the number, the dimmer the star. 11th magnitude is 100 times dimmer than 6th magnitude, and that 11th magnitude star would also be 10,000 times dimmer than a 1st magnitude star.
Couple of things to notice. First of all, it makes sense that they would need to extend the scale towards dimmer stars once astronomers are able to use a telescope. Why would dimmer stars appear with a telescope? Well, remember, the telescope helps you see objects that are farther away. So these farther away stars will be even dimmer. The other thing to notice is we're going by powers of 10 is what he's pointing out, right? If you are a level 6, you are 10 squared dimmer, 10 to the 2nd power. By the time you get to a level 11, you are 10 to the 1, 2, 3, 4th power dimmer.
In the other direction, we have some objects that are brighter than 1st magnitude stars. Hipparchus actually fudged the numbers a bit. The star Sirius in the winter sky is definitely brighter than most other bright stars, and it shines at magnitude negative 1.4. The planet Jupiter is even brighter than that, often appearing at around magnitude negative 2, and Venus, brighter still, typically around negative 4. When objects are bright, they are denoted on star charts with larger dots. Dimmer stars are usually given smaller dots. This helps us locate brighter objects in the sky more easily. But from our perspective, even brighter than the star's magnitudes is that of the moon and sun. The full moon in the night sky shines at magnitude negative 12.7 and the sun at magnitude negative 26.7. Those are both really bright compared to starlight, but also a huge difference even between themselves, as the sun is 400,000 times brighter than the full moon. Now, everything we have discussed has been visual magnitude, meaning how bright or dim objects appear from our location right here on Earth. Now, another concept that you may run across is absolute magnitude, used by astronomers to compare the relative brightness of objects when placed the same distance. But that's a little more complex than what we need to know for simple stargazing purposes. All you need to know about it is that it compares the relative brightness of objects if they were all viewed from the same distance away. However,
So that part should sound familiar, but now what he's going to do is he's going to take you to a night sky and apply the idea of apparent magnitude, which is cool.
for visual magnitude, it helps to understand how it relates to other objects besides stars. Stars are point-like objects in the sky, so it's easy to assess their magnitude and brightness. But galaxies, star clusters, and nebula are not quite as simple. So we look at their integrated magnitude. That's a way of saying that the same magnitude is now spread out over a larger area.
Don't worry, you don't have to define integrated magnitude. It's just interesting to know that the deeper you get into a subject like this, the more special vocabulary there is.
For small objects, that can mean it is something that will look brighter to us in telescopes. If the area is very large, though, such as the galaxy M33 or the nebula M1, these objects may look very dim, relatively speaking. If possible, try to look for the surface brightness of an object. Objects above a surface brightness of 11 or 12 can be very difficult to find, particularly from light-polluted areas. That's a quick overview of the magnitude scale and how to understand it.
And that is where our science stops for the day as well.